Today, I'm going to talk about the strengths of materials. In most of the analysis, we assume that the materials behaves as a linear elastic material. But this is not necessarily the real case. Here, I present the different cases of material behavior. So linear elasticity is the simplest case when we can have analytical solutions in some cases, and the numerical solutions behaves well in most of the cases. But we can have nonlinear elasticity that is shown here, where the material can recover the full shape after deformations, or we can have a viscoelastic behavior when the material can recover the original shape, but can have a loss of energy after recovering the original shape. This is the case of elasticity, but we can also have a plastic behavior. Plastic behavior is when you have permanent deformations in the materials. And we have a case here that is called perfect plasticity, when the materials yield at this point. After this point, all the deformation is plastic. Or this is more realistic case, that is a strain hardening behavior. That means that the material will reach a point, a yield point. After this point, part of the stiffness is going to be lost, and the material will have an elastoplastic behavior. Some of the deformation will be elastic, another part of the deformation will be plastic. This is a very particular case, mathematical approximations, where we assume that the material is rigid until the yield point, and then after this point the deformation is completely plastic. So when we talk about yield points where the material becomes partly plastic, or failure when the material cannot sustain more strain, in these two cases we need to talk about strengths of the materials. So let's start talking about the strengths of the concrete, very much used materials in civil engineering. So the compressive strength of a material, like concrete, is the force per unit of area that it can withstand in compressions. So let's consider this experiment. So to measure the strength of the concrete, you do this uniaxial test. So you put the concrete specimen here. So you fix at the bottom, you apply a load, and you move this load with a constant velocity, very low velocity, and then you measure at which point the material breaks. So this is one example of the test. This is with the cylindrical test, but you can have also a cubic test. So this is a typical behavior of the stress strain, where you can see here that the stiffness is reduced, indicating some yielding or plastic deformations. It's going to reach a point when the material cannot sustain any more stress, and this is going to be the failure point. So in this case, of compressions, correspond to the compressive strength of the concrete. So how do we get this compressive strength? So in the cylindrical test, it is assumed that it's 90% of the maximal strength in this test, and in the cubic test, it is assumed to be 72% of the strength. So the tensile strength is the strength of the concrete when it is subject to tensions. This is an empirical formula that gives us the tensile strength in terms of the compressive strength. There is another important aspect of the behavior of the concrete that is very relevant, is the creep of the concrete. If you put the concrete with a certain load, the strain is not going to be constant on time, but it's going to be a small change of strain on time during the years. So this change of the strain corresponds to concrete creep. It happens in the concrete and it happens also in timber. The strain will increase under constant load in a very small fashions. To see significant change of strength, you have to wait many years. This is creep. Steel is another important construction materials, and the tensile strength is the stress that the steel can withstand under tensions. To measure the tensile strength, you use this apparatus. This is the specimen, and you move these two parts apart with a constant velocity, and you measure the force. So the typical stress-strain behavior is like this. So you have a perfect, almost perfect line where the material, that is the steel, is linear elastic, and there is a point when the material became plastic, that is the yield strength. And then it's going to reach a point where the material cannot sustain any more stress, that is the ultimate strength. This is the point, D. But if you control the system by strain, there is another point when the material cannot sustain any more strain, that is the fracture. So, and also you have an area. This area corresponds to the modulus of resilience of the strain of the steel, and all this area is the modulus of toughness, tough. So how tough is the material is related with this area under the stress-strain curve. So we have yield strength that is correspond to this point. So we have ultimate strength that corresponds to this point D, and we have also endurance limit. What is the endurance limit? Is approximately 50% of the ultimate strength, and is a limit below of which the steel is not going to have fatigue. So you apply cyclic load in the cyclic load, repetitive load in the steel, the material may break, but if this load have an amplitude that is lower than 50% the ultimate strength of the concrete, it probably is not going to yield by fatigue. So considering this limit is very important if your structure is subject to cyclic loads. So the next material is the granular media, like soils, clays, or any material consisting of granulates. In this kind of materials, the failure happen on shear deformations, and we define the shear strength as the maximal shear stress, after which the material will fail by shear. To measure the shear strength, we use this shear box. So we put the granular media here, and it has two parts. One is fixed, another moves. We apply a normal force here, and we move the upper part with a constant velocity, and the typical stress-strain relations is this one. So this is the shear stress, and this is the displacement of the top part. And we observe here elastoplastic behavior until one point, that is the peak strength. And after this point, the soil is going to soften, and it will reach a limit behavior where we have a residual shear strength that is called tau R. So these are the two quantities that characterize the strengths of a granular material. The experimental behavior of this strength is represented by the Mohr-Coulomb yield criterion. So this is the peak shear strength is related with the normal load that I apply here in the shear box. And there are two strength parameters, that is the cohesion of the soil and the angle of friction of the soil. So it is important to understand that this yielding or failure doesn't happen globally in a structure, but is going to happen in a particular point in the structure. It's going to start in a point and it's going to propagate probably from this point. So we need to check if the material is yielding or failing by monitoring the stress in each point of the structure. But you don't need to monitor all the components of the stress, but only the invariance. So what is invariance? So the stress tensor is a symmetric tensor with 6 independent components that can be represented like this or like this. This tensor is symmetric, and since it is symmetric, you can find a local coordinate system in each point where this tensor is going to be symmetric, like this. So in this coordinate system, you only have 3 components that are the 3 principal components of the stress tensor. Now I can define with these 3 components the stress invariants that are the mean stress, or also called hydrostatic stress, is the average of these 3 values. So the von Mises stress or deviatoric stress is this quantity, and the other one is the load angle. So these 3 components has a geometrical interpretation. So this is the space of the principal component of the stress. It's a 3-dimensional space. And we can define here a line that is the line where all 3 components are the same. This is a straight line in this space. Every point of the line have a perpendicular plane that is called the deviatoric plane, where the sum of all the 3 components are constant, where the mean hydrostatic stress is constant. So the idea is that every point here, every stress point, can be projected over this hydrostatic line when all the components are the same, and the distance of this projection to the center is the mean stress, and the distance of these projections to the actual stress point is going to be the deviatoric stress. Yes, so it's difficult to see, but this point is in front of the point where all the stresses are equal to 0, and this angle in the deviatoric plane that is represented here by a circle, so is the actual stress, and this angle is going to be the load angle. In terms of the principal component of the stress or the invariance, we can define the yield criteria or the failure criteria. So the first case is when the yield criteria, the yielding or the failure, doesn't depend on the mean stress. One of these examples of models of failure correspond to the Tresca yield criterion. So you have this. This is a surface. If the stress is inside of this surface, it's elastic. If the stress reaches the surface, it becomes elastoplastic. This is the Tresca yield criterion. So this has a single material parameter that corresponds to the compressive strength. And it can be improved by the von Mises yield criterion. This can be represented by a smooth surface like this. This is the von Mises yield surface. So if you project this surface in one plane, this will correspond to the plane stress analysis. So it's easy to visualize here the yield or failure. So von Mises will correspond to the intersection of the surface with the plane, that is a ellipse, with a compressive strength that is going to be the same as the tensile strength, and the tresca will correspond to a polygon. So you can see that von Mises is a better option because it's a smooth surface. So this criteria is used in steel because the yielding point or the failure point of the steel doesn't depend on the mean stress. There is another model for yielding or failure where the yield or the failure depend on the mean stress. This is the Mohr-Coulomb yield criterion that we already introduced. So if we express this criteria in the stress space with the two material strength parameters, it's going to correspond to this geometrical structure that is quite complex. This is the Mohr-Coulomb yield surface. Simplifications of this surface is the Drucker-Prager criteria, where this structure, pyramid structure, is replaced by a cone. It's going to be better because it's smooth. So this is the projections of these surfaces in the plane that correspond to the plane stress analysis. So this polygon corresponds to the Mohr-Coulomb. This polygon gives you two different values. One is the compressive strength, another one is the tensile strength. You can optimize this polygon by ellipse, and then you can convert this Mohr-Coulomb yield surface into a Drucker-Prager yield surface. So this one is going to be better because it's a smooth cone. Give you a better descriptions of the yield or the failure. So this criteria is used mostly in soils because soils satisfy this Mohr-Coulomb yield criterion in a high degree of approximations. So Drucker-Prager criteria is a very robust criteria because you can see here that von Mises is a special case of Drucker-Prager when the angle of this cone is 0. Also, there are some important formulas. So this is the equations of the cone. This is the Drucker-Prager criteria, and you can calculate these two parameters. Alpha is related with the aperture of this cone, and K is related with the apex of this cone, this vertex of the cone. So you can calculate these two quantities in terms of the cohesion of the soil and the angle of friction of the soil. This formula is very useful. But if you want to use the Drucker-Prager criteria for concrete, so you have to relate these two parameters with the tensile of compressive strength of the material. So this is the formula. So I give you the two parameters of the Drucker-Prager model in terms of the compressive strength of the concrete and the tensile strength of the concrete. However, the Drucker-Prager criteria have some limitations in the modeling of the concrete. So the Drucker-Prager surface is different to the actual surface, yielding surface of the concrete. So you can see that it's not really a cone, it's like a potato. So if we do a cut in the deviatoric plane, we obtain that this is the Mohr-Coulomb criteria, and it's different from the more advanced model that represent the real data. Like here is represented the Ottosen criterion or the Barcelona criterion. Major difference you can see in the plane stress analysis when we assume that one of the components is 0. So it's going to be the intersection of this surface with a plane. So these intersections is represented here. So this is the envelope feature for plane stress analysis. So the points, the black points correspond to the experimental data of Felcher, and the green line correspond to the Mohr-Coulomb criteria. And the other two curves correspond to Ottosen or the Barcelona criteria. So you can see that the Mohr-Coulomb criteria doesn't reproduce very well the data here, but it provides a conservative descriptions of the Felcher of the concrete in different load paths. So in summary, if you are modeling steel, it is recommendable that you use the von Mises criteria, and if you are working with concrete, it's better that you use the Mohr-Coulomb criteria for conservative predictions of Felcher.